headphones. Oh, there we go. Oh, you got a picture of yourself. Thank you. Can you hear me?
Yeah, I can hear you.
Yeah, we can hear you. But your mic keeps making weird noises.
Can you hear me?
Yeah, we can hear you.
No?
There's just a lot of
You can't.
noises sometimes.
Oh, thank you for shaking your head, gosh. All right. I said, Yika, I don't know if you could hear me before, but thank you for getting a picture. Oh, it helps. All right. So I don't know. Does anyone have any questions? Okay, I failed to get the last lecture up. All kinds of things came up, but you might, let's see, let me put it in the chat, and then I'm gonna add this to the homework or the readings on the web on the course page. But I think it's page 185. To $198, and that's about typed bump. So bump is the programming, what he calls the latest programming language that we've been working on, which has parameters. And I don't know, I've been jumping all over this thing to talk about it today, but I didn't really figure out what he's doing in terms of the semantics of call. I will have to look at that. Maybe we can tell. So, you know, and I don't know, reading, you know, to me, the major weakness of this book is that he hasn't stressed typing, and he waits until chapter 13 to do it, which is like insanely late. He's done all kinds of other off-track stuff about concurrent programming and pi calculus and everything. It's like it's a almost like it's like an afterthought or something. Oh, by the way, I should have done something about type, so I'll add it in chapter 13. Oh, chapter 14 has lambda notation. So, but you also, you know, for me, who's read this stuff for years, so there's a long time, there's a long time debate among computer scientists about types. And in general, I think, you know, it's, you know, like close to the metal hackers disdain types, but software engineers embrace types. And unfortunately, in languages like JavaScript is essentially untyped. Although one of the fastest growing languages is called TypeScript, which is essentially a Haskell-like language that compiles into JavaScript. So and it works well with React. I don't know if you know those things. I don't really know them, but I know that's true. So it's kind of a long time debate, and I have to say, I think Huddle, which is unusual for a programming language semantics guy, seems to fall on the leave it untyped side. Now, the nice thing in Haskell is a lot of you may forget this, or kind of like it never really sank in. You don't have to write down the types of the functions when you declare them. Haskell figures it out. So you can write code that has no type declarations in it. Now, it often makes it easier to read code if type declarations are there. But it also, for me, often ends up in an unwanted error because I didn't make the type correct. Like, for example, if you want to do insert on a map data type, the domain of the map has to be an ordered type. Otherwise, insert doesn't work because they're using a balanced binary tree. So they need to go, okay, does this entry go to the left or does it go to the right? Where does it go? So balanced tree representation, you need to have an ordering on the keys. And so if you don't type in that constraint, they're ordered, whatever it is, or if you use your own type and you didn't derive ord as it's ord, it's not ordered, it's ord is the keyword for that, then it'll tell you have the wrong type. And I also know that a lot of you don't actually read the error messages. Like if you just see an error message, you just freak out and start trying to program something different to not get an error message. But if you read them, and they are a little bit annoying to read, but like if you pay attention and you read them, they oftentimes tell you exactly what's wrong. So anyway, that's kind of like, the picture. So you've got sort of like the group that prefers untyped programming. Okay. And then there's, Ruby. Has anyone used Ruby? Holler if you used Ruby. It was maybe a little bit of a flash in the pan, but maybe about 8 years ago. Like it was just the killer language to know for writing web apps and other things. Ruby on Rails. I don't even know what that means, but it's like, oh, Rails was like some package that Ruby was using that made writing web apps amazingly fast and ingenious. And we did have like this student in our program around that time who I don't even know. He may have like he learned Ruby on Rails. He wrote some really amazing application using it. And when I talked to him, he's like, "Oh, I couldn't have done it if I wasn't programming Ruby." Um, and then I think he got a job and quit, which is something I don't recommend. Like unless you absolutely, unless you absolutely are starving to death, don't quit. It just takes longer. I quit my own education like numerous times. Like I had a child, and so then it was like, okay, I better get a job. And then I went back to school and I got a good job. But every time I went back to school, and got another degree or got more education, I got paid more and I got a much more interesting job. So when I look back over it, okay, I worked a lot in there. But if I look back over it, if I could have compressed it, I would have started at a better level sooner, at a higher level sooner. Um, and so that, that might have made a difference overall in my lifetime pay because I would have been getting paid more earlier than I did. Um, I don't know. I'm kind of rambling, but okay. It makes me think back though to like when I was a C programmer, and C was in the early, it's untyped. You could run this program called lint, like, oh, you're just picking a little bit of lint off your jacket. Lint would check and sort of do a little bit of a job of type checking and tell you, uh-oh, there might be a problem here. But lint was kind of like a weak type checker. Now, the reason I know it, and I wish I could just erase it from the book, although it's good to know, but this is like an argument that at the end of this section I just asked you to read, which is on the typed bump language, he has a whole section. He ends it, the limitations of the type system. And the upshot is that if you look at the Venn diagram of programs that will not crash because of type errors, that completely contains the Venn diagram of the circle of the collection of well-typed programs. So in other words, there are some safe programs which are not well-typed, like they're not actually going to crash. And that could be because of some runtime property. But in general, types prevent you from writing bad code. In fact, we're doing this project in the IOHK lab where we're taking this language, which it's a subtle, it's maybe a subtle point. It's like they've written a language that's embedded in Haskell, so it's a Haskell data type, just like our STM and A expression and B expressions are. Those are just data types, right? And then we write the semantics, which we can turn into an evaluator. And so then we have an evaluator for that piece of syntax. But so they use the fact that it's written in Haskell, and it uses the fact that Haskell itself is strongly typed. But we're implementing a programming language which Haskell can't guarantee that the programs in the language that we're writing in, called Marlow, are strongly typed. And we've run into, and then we look at the evaluator code, and I'm just reading this fascinating paper. I don't know, what is it called? Ghosts of Departed Proofs. On how you can enforce certain constraints that, like in Haskell, if you apply the head function to a list, if the list is empty, your program crashes. So then you could have you could be really safe and you say, okay, oh, we'll make head return a maybe A instead of an A. Well, that means then the programmer has to deal with all this nothing and just and nothing stuff, which is just kind of pushing the problem down the road, but the library writer feels safe because none of his functions will ever cause the system to crash. Anyway, all right, so let's look at type checking. It turns out it's it's really easy to do. I think it's easier than the semantics, or as easy as the semantics anyway. So it doesn't, I can't really understand why you wouldn't want to type check it, but okay. maybe not. Now, what are the kinds of things that it can catch? The type checker is that the type checker can catch things like, oh, you call a procedure that wasn't declared. There was no declaration for the procedure. What's going to happen? Your program's going to crash. What could it do that would be sensible? There's not even any sensible default behavior in that case. Oh, I don't know. Some untyped people might say, like, oh no, you could make it the identity function or something. I don't know. So if you made like the function that isn't defined equal to the identity function, but then you could write all kinds of obfuscated code that no one will ever understand. So anyway, let's look at, so I'm going to start going through this. If you have your book and you go to page 185, you can, you'll be in the right spot. Oh, I don't want that. I want to share my screen. And I want my Emacs up. Where is it? Oh, God, who knows what I'm going to reveal? I had to, this thing is getting recorded. I'm like, oh, my God, what, what have I've been showing my email? I'm like, gee, that's probably not that good of an idea, recording my open email. Okay, so here's what I've been looking at is I've been writing it down for like about the last half hour. After at first I started saying like, okay, I'm going to write down the type checking for bumps, and I spent 30 minutes doing that, and then I realized, he does do type checking later on, but I thought it was for a later language. And I thought it was worth showing it for this simpler language bumps. And in fact, he has it. Again, we'll look at some points. I object about some of the things that he does, but okay. Some of them are just matters of taste. So anyway, one thing that he does here is he gloms together. This used to be A expressions and B expressions. See, here's the B expressions. And here's the Boolean expressions, and here's the arithmetic expressions. And then, he allows parentheses, although that's a typo in the book because he has it twice. He just cut and pasted the line and changed the B's to E's and the A's to E's. Now, one interesting thing about this is, well, we'll see in a bit that this is interesting because it's nice to have, equals for both Booleans and for integers. And so we're going to have a stronger kind of system here where we can do that. And so we're going to have to, the typing rules will take care of making sure, like, for example, on and, these have to be Booleans. We're not going to do like, did I give you a homework earlier where I asked you to change it so that you could interpret integers as Booleans? Here the type checker is going to make sure that both E1 and E2 actually are Booleans. And it's not going to be some kind of weird interpretation of integers as Booleans where 0 was false and everything else was true, which is what they do in C and C++. So we have this one class of expressions. Maybe I should put this in like this. So we just put them all together into one syntactic class. Statements look the same as they did before in bump. And, remember his declarations are a little different from the 4780 ones that I've been presenting, because I like to have the semicolon thing here as an actual operator on declarations. But we'll look at his rules. But I just wanted to remind you these, and we could write the typing rules for these very easily also. It does make one change, is that he's got this epsilon type, because that's his end of list. And, you know, we might want to have a begin end block with an empty, with no declarations. So I made a new type called decl that's either an actual declaration followed by a semicolon, or it's an epsilon. Now we could also make a semantic description of, you know, for something like of the form D semicolon S, where D is a declaration and S is a statement. And I mean, that would be sort of the same as this. So then you could have, okay, compose a declaration with a statement, and that's like a begin end block, or just have a statement, right? You don't need the declaration, and that's the rest of them. So I don't know. Any questions? This all should look familiar. Now, one thing is that the semantics are going to change a little bit of the language, because he's also allowing for Boolean variables now in the language, in the real bump, in the language that we were doing, you know, way back in whatever it is, chapter 7. In the real bump, you can only have integer variables, but now we're going to add the possibility of having Boolean variables. And so if we're going to be type checking, we have to add some syntax for types. And so he calls this type, the B, as, which is kind of like the you know, the ground types, or the constant types are int, which are integers, and bool, which are booleans. You know, actually, this won't fly in Haskell, will it? Because, you know, those are already type names. Maybe you can put them as constructors, though. You can. Okay. This is the type name out here. This is a constructor name. I think you can do that. And then T is a more complex type. So it's either a B, so it's either an int or a bool, or it's of the form something like X colon B arrow OK, where X really is like an identifier. Right? So he's kind of like writing the syntax in this mixed way, where he's putting real type, you know, the type, you know, types in here. Anyway, this is going to be an arrow type. Now, the OK I find a little bit strange. He's going to use OK when he sees a procedure declaration that's correct. Now, and so what it's going to be is that it's really going to be, I mean, maybe I should call this P, because this is always going to be a P name. It's always going to, remember, P, we had a type var, which is, you know, identifiers for variables. And we also had p names, which are identifiers for procedure names. And so here I could say like P, it comes from P names, because that's the only time you're going to get a function type. See, this is supposed to be a function type like we're dealing with Haskell. And if you think about it, what is a procedure? A procedure is something that takes, now it's going to take either an int or a bool, and it says, okay, I'd rather see him say, oh, returns a type called STM, and we make STM one of the types up here. So it only works if it returns, because the way to think about a procedure declaration is, you know, you've got something like proc px is s, is that this is a function. So whatever the type of t is, and he labels it. He says t x, and this is t is a type. So he's saying, okay, x is some type, and I'm telling you in the declaration you have to tell him what the type is. I think we don't need that because we could infer it, but okay. And so what does it do? It takes, like, if t is a bool, this is a function from bool to statement, because the body is a statement. And if t is an int, so I guess maybe I want to add statement as one of the types down here, not up above. So I don't know. You run into issues in the Haskell type system where I want to say something like this, but I can't. I could only put a T here, and then we would have to verify that. Where does he put OK? I looked, and I don't think he says where OK is. He just uses it. He doesn't put it into a syntactic class. Okay. In his rule, he says OK. So we can do that. Although it would make sense to have that say statement there and add state, you know, like you could add just, well, it really is the syntactic class statement. So anyway, he uses OK. Any questions? So the types of procedures are going to be functions. That makes sense because our procedures are parameterized by a function. Okay, so now he calls these type environments. They're sometimes also called type assignments to kind of distinguish. Whoops, what's caps lock? To distinguish, you know, sometimes they're called type assignments to distinguish them from an environment which typically has to do with the semantics, and a type assignment which has to do with the typing. But we're okay. That's fine. Because it is, I mean, you know, underlying, if you're untyped in your, in your epistemology, in your personal epistemology, you don't like types, here we go. It's a function, it's a finite function. He actually makes it more technical. He says it's a partial function from var union p names arrow t. And I kind of prefer to think of it as a finite function that you're going to build up. It's only going to have entries in it for the things that you've actually seen declared, and no program could ever have an infinite number of things declared. So it seems to me more precise to call it a finite function instead of saying it's a partial function from var union p names to t types. So it tells you the type. You give it a name, and so we don't need separate ones like we do for, so there's, you could think of, what is var union p name, var union, note that var union p name is just a subset of identifiers or strings. But we don't care which name. Depending on the name, we're going to tell you the type. Like, we don't care if it's a variable or if it's a procedure name. So really what it is it's a finite function from identifier to t. Any questions? So, I don't know. I used to always say, like, okay, like, people get confused when they see these different things, env, sto, and now he writes capital E's for these in type environments. What are they, what are they for? What are they? Why do we have these? Well, what they're for is they're data structures to help us remember, in this case, the types of the various declared things that we've seen. We're going to be able to look up and say, okay, P, oh, that was P was a procedure from int to okay. Now that's why I'd like rather say, STM here, but okay. It's a procedure, or okay, oh, wait a minute, X, oh, that's an int variable, or Y, okay, that's a bool variable. So it's a data structure that we're using as we go through the program. We build up the type environment to keep track of the types of everything that we've seen. Now, what do we use the environments for? Environments are used kind of in the same way. The meaning of a declaration is the environment. And what does the environment do? The environment remembers the meaning of two different things: proc. The proc part remembers the meaning of a procedure, and the meaning is more complex than this T thing. So this is kind of similar to the regular environments that we've been using to remember the meaning of procedures and the meaning of a variable. And the meaning of a variable is a map from identifier to locations. And so then a store is another data structure that we're using to remember the meaning of what's stored in a particular location in memory. So you can think of environments in the store as kind of data structures that are being used to remember things. Does that make sense? I can't see enough people. For some reason, I can't I guess I could do it differently. I see. I could stop share. I could shrink this down a bit. And then I think, can I say share? Oh, I could just do this. Now I can see most of you, not all of you. All right, I'll share. One thing I can't see is chat. Okay, I might be able to pull that out and then share. Aha, now I can still see the chat. Okay. I'm slowly figuring this out. Now that we're almost done with online classes. Okay, so these are the type environments. And, you know, he writes this a little bit different because he doesn't trust the readers to know anything about higher order programming. So he says, so first let's read this one. It says E, which is a type environment, and I should put over here E with X maps to T is equal to, now remember, E is a function from identifier to T types. So E is a function. And so what we say here, we say, oh, it's the function lambda y, and you look, and so now this is a new function. So what happens in E if I look up X? What in the old E? Well, it could be there or it might not be there. And if it's not there, it's an error, program crashes. If it is there, it could tell me something, but you know, what if I write var, I mean, it depends on whether we can avoid, our type checker could avoid this. Right now, we could write something like var x gets the value of 0 equals 1, semicolon, and then I don't know, some way down in the program, let's say, I say begin, and then I say var x colon equals 7. Now, in that case, we will have built up an environment that knows something about X, but when we do this pointwise update, it would change the type. So in this case, if after reading this point, we would have built an environment that if I said to you, ask the environment, what's E of X? It will say, oh, that's a bool, because the type of X is bool, because this is a Boolean expression. But then when I got down here after this, if I entered now, okay, in E that X is an int, from then on, it's going to think X is an int. Does that make sense? Letitia, does that seem sensible? Good. Okay. So, this is a new function. And what does it do? It just looks up and says, okay, it's expecting it gets an input y, which is an identifier, and then it checks, is y equal to the one that you had before that was the updated one? If it is, then you return t. Otherwise, you do exactly what the old e did on y. You just apply whatever e was on y, and that's how you do this. Now, that's a function update. I mean, a finite map, no matter how you implement it as a list of pairs or a Haskell map or a Java dictionary or however you choose, or I don't know, you could make up your own, or you could represent it as an actual function. But however you do it, you need some kind of pointwise update operator, and you also need to be able to look things up. And I think, as we'll see below, we may need also to figure out which things are in the domain of this finite function. Questions? Okay. Now, this is a weird word, judgment, but I mean, I don't know, I wonder who, Martin Loff, like he's a Swedish logician and philosopher, I think, made up the term with judgment. And it's basically that, when you write something like this down, it's a judgment. And the judgment that you make when you write this down is that expression E has type T in type environment E. So this is the capital E is the type environment. E is an expression, and we're claiming it has type T, which means it's one of these things. So it's either int, or it's bool, or it's p colon b arrow stm, or or okay. I mean, if you want to do it his way. So a judgment is, when you write this down, you're kind of claiming, I don't know how to turn off my notifications from Slack. Oh, God. All right. So you're claiming this is true. Stop. Stop doing that. I'll say in class, I don't know. I'm teaching eager students can't come. Okay. Oh, God. Okay, he smiled back at that. So anyway, I don't know. I mean, he makes a distinction between a judgment and an axiom instance and so forth. I mean, you could sort of think, like, if you write this down, what we're doing is the proof rules justify the truth of the judgment, and that's what they do. They're proofs that the judgment is true. So anyway, if we want to verify that if we want to check that the variable x has some type in this type environment, he writes this rule like this, which I don't know, most people might write it with this as a side condition. They might say like, okay, that's true if this is true. But he writes it actually above here. But what does that mean? That means that if I apply E to X, it tells me that in the environment E, X really has the type T. And that's what I'm trying to claim. I want to claim this. How do I know if it's true or not? I look up X in E, and if in E it comes back and it tells me, because remember, this is the thing that's going to return T. E applied to a variable is going to return T. And so you look and you say, does E of X give me the same thing as T? Is that okay? Someone say something. Is that sensible?
That's sensible to me.
Someone say it's not sensible.
It's not sensible.
I'm not getting anything from you. I can't hear you, Parker. Are you speaking? Huh. I didn't hear anyone. That's weird. Somebody say some, All right. Isaiah, you're not a chicken. Go ahead. Talk to me and let me see if I can hear you.
Can you hear me, Professor?
Wow. I'm not hearing you. Hang on. Try it now.
Hello, hello, hello.
Wow. It's really muted. What's going on?
Try checking your settings in Zoom itself.
Yeah.
I think there's a volume setting in the Zoom settings.
Okay. I barely heard that, but that's good. Okay. Clear that. I don't want that. Let's see. Stop share. All right, I'm looking at my settings or looking for more. Nope. Breakout rooms, caption, chat, participants, stop video. That's weird. Where is that button? I don't know. I'm thinking it's my sound on my. It's way up. Try talking again, Isaiah.
Hello, can you hear me?
Not very well. Let me just try.
I should have a soft voice, maybe.
All right, try it now.
Can you hear me?
No.
Hello, hello.
Try it now.
Hello, hello, hello.
Can't hear you at all without my headphones. All right, whatever. Sorry. Maybe you've all been conversing with me and I had no idea. All right. Share screen. Okay. This will avoid at least the Zoom or Slack messages coming through. I'm just sharing the Emacs window instead of everything. All right. So that's how we check that a variable is well typed. And now how do we check that an expression E1 equals E2 is well typed? Well, first of all, that thing should be a Boolean expression, right? That was in our old B expression language. And we used to have two roles because we had one that said that they were both A expressions, and the other one that said they were both B expressions, kind of to evaluate them. But now the type checking, we've reduced the rules by saying, okay, look, in E, if I can tell that E1 has type T, and also in E, I can tell that E2 has the same type, then I know that this expression has type bool. Now, I guess maybe I skipped over this over here, and maybe this might be worth looking at, is that you might be going like, well, wait a minute, what's going on here? If we were, this is like a big step semantics. And how is this a big step semantics? Well, you could think of the colon as being like an arrow. And so it's like X evaluates to T, but colon is the more traditional notation for types. Yeah, that's a good question, Parker, whether my Linux sound outputting to my headphones, and it was. I mean, that's what I've been checking, and it seems like it is, and the volume on my thing is up, so I don't know what's going on. Anyway, yeah, that's a good thing to check. So anyway, we could have written this instead, and then it would be using the arrows that you're maybe more used to. But so, like, what is, gamma here? What is the set of possible configurations? Well, it's let's see, what is it on this one? It is it's expressions. What does he say? It's expressions union together, so it's EXPR, union together with real integers, union together with real Boolean values. And then what is arrow? Arrow is a subset of we have on the left side an expression, and on the right hand side we have int union bool. And then the set of configurations T, which is, and we're using T in multiple ways here, is int union bool. That's the terminal configurations. So this is how this, he writes it out. He says something like, okay, the transition system is Wow, Tarantino system? Wow, I can't even get it from that terrible spelling. The transition system is, and then he would write left paren, this, and then he just says arrow because we're going to define it below. But that's funny. He calls it arrow, and it should really be. Oh no, this is modified semantics, but still, we've got colon in this case, and then we have the final states are int, union, bool. Does that make sense? So on the left here, we have an expression. That's a a variable. On the right, we have, so this is really colon. On the right of colon is a subset of, it's on the left, it has an expression, and on the right, it has an int union bool. And that's it. That's what is a subset of T. It's just these two. I mean, maybe I could say it's, well, except that, yeah, so, okay, really, I should say it's B, where B is the, all right, so maybe there was a error in what I was just saying, because it's not really ints, it's the syntactic class of types. And I wish he had called this something besides B up here, but that's what he called. So you have expressions and types, but in the colon relation, the expression is the thing on the left and the type is the thing on the right. So we're really only considering this thing. And like the other rules, he considers this E to be something outside the arrow expression. Even though it's used to determine the truth, it does not change in any way by the type checking rules. All right, I'm going to assume I'm beating a dead horse here and keep going. So what is like a typical rule looks like, E, like let's do something more standard, like, let's do E1 and E2. Well, we want that to be a bool. And so when would this be sensible as a bool? Someone tell me, what are the types? Nobody's telling me, or I can't hear. Let me crank up my ears.
They're the Booleans.
Yes, right. It doesn't make sense to apply, and like if I put here int, that would be crazy. I can't do a conjunction on an int, a logical and. This has to be bool. Now, what does he use for and? I mean, I thought of using you know, this as an and symbol. Do you like that better?
I like the ampersands.
Yeah, it looks, the ampersand looks more like, all right, looks more like the Haskell notation. What about like, you know, another one would be like, so actually, and is a Boolean operator. That's the only binary Boolean operator that we have, because equals could have different kinds of arguments, but and expects them to be the same. And of course, you know, I don't know, I could copy this one maybe and make something, type a little bit less. I don't know. What about not? So not E, lowercase e, not expression E, has type bool if and only if E has type bool. What does he call that one? And EXP. No, yeah, and EXP. So this is all on page 191. So there's other rules there too, but they're mostly boring, right? The only one that really is interesting is this one, I think, and this one. And so now we could take these rules and let's do an example. We could say, try checking using the rules to check, I don't know, you could try to check something like P, you know, like suppose that assume that E is equal to the map that takes X to int and takes Y to bool and takes, I guess maybe that's enough, and try to show something that, let's try to show something not true, like that E shows that X plus Y, whoops, is an int. But the rule for X plus Y would be like the rule for, well, I guess I could write it down because I didn't write down a binary rule for the old A expression operations, but it would be exactly like this. And now some of you are going like, oh, how does he remember this? It's dead trivial. I'm not remembering it. I'm looking at it and saying, what does this mean? When is E1 plus E2 sensible as an int? Oh, it's sensible if E1 is an int and E2 is an int. So here I look and I say, okay, show that E1, using E, show that X is an int And that's only true if E applied to X is an int, which is true. And then on this side, I got to try to show that using E, show that Y is an int, because that's what the rule says I have to do. And when I look it up, though, I get back E says Y is a bool. So this branch fails. But we could show, for example, that X equals X and Y is a bool because I could show that using E, I could show that X equals X. That has to be a bool. And over on this side, what do I have to show? I have to show that E can prove Y is a bool. So go back over here. The rule for equal says you got to be able to show that each side is the same. And here I can say E shows that X is an int. Because E applied to X is equal to int. And on this side, I have to show again that E shows that X is an int. And that's true because, again, you know, E applied to X is equal to int. And down here, now this is true because E applied to Y is a bool. Is that good? Oh, and these are, these are true. So I should, I don't know. I like closing off the tops of my proofs with lines so that I can see, okay, everything ended up being true. So I like to put lines over my axioms. So you can look at these proofs and see, okay, everything turned out to be true. All the leaves of this tree, this upside down tree, are closed. Okay, that's the application of those rules. Now, oh, we only have 5 minutes. Let's look at one of the, well, let's look at, we could look at the proc rule. So what did we have up here? We had, if we use his language, consider declarations. Okay. So what would a rule for proc P and then this ugly T, which I don't think we actually need, but okay, let's I guess let's do it the way he wants to do it. Oh, he still has this DP thing. Oh God. And he wants to say, that's okay. If what? He says, that's okay if when you take E and you update P to be, I'm sorry, you take to be a map that says X colon T arrow okay. So what is this saying? This is saying that, okay, that variable X has type T and is okay. And if you can show with that that DP is okay. Now, well, yeah, maybe having the type around is better. I mean, syntactically, I'd far prefer to do this, though, and say, you know, like X colon T, like it is in every programming language you know, but all right. We can write it like that. So this means this procedure is well typed if using E. Oh, wait. Why is it? What did this looks wrong to me? What about S? I think you also have to say using E and assuming that X has type T, you can show that S has type, and I don't know, what does he do for statements? They're okay also. So I have no idea why this is not there. There are a lot of typos in this book, so this could be that. How could that not be there? Yeah, you know, someone ought to look up the errata for the book and make sure. I think this has got to be there. It can't be that you have to check that S is a well-typed statement, or else this procedure can't be okay. So S has to be a well-typed statement. But to show that it's a well-typed statement, you get to assume that, okay, X has the type T. And then the call rule is the other one that would be of interest here. And it would say, okay, E shows that. Now, maybe he does it here. That would be weird, though. Call. No, he doesn't do it here. So he says call P with some expression is okay if there's two things actually you have to show here. You got to show that E really is an expression of type P of the right type. So you got to say that E has to show that P has type X colon T arrow okay. So in other words, you have to have an entry for that. And I assume that he wants to add something in there that he doesn't have, that I don't see, which is that, okay, that means that that's true if he might really want to say something here like E of P, E applied to P is equal to this, and that E shows that the expression E has the type T, has the right type to be as input. Okay, sorry I went over. So I'm changing that. This is definitely different. But anyway, all right. I will, whoops, I'll save this file. Oh, that's interesting. Okay. And I'll upload it hopefully right after this. Although I have office hours again this afternoon. Does anyone plan on coming? No. All right. See you all later. Bye.